Hello everyone, I'm Hazarapet, machine learning scientist from PicsArt. Today I'll be speaking about specialist diffusion model, a text-to-image diffusion model which aims to learn any unseen style. If you're familiar with the computer vision models, back in 2010, 2015, for every image we try to detect a class, detect a bounding box, or set of classes. So it means for every image we kind of give descriptive information about the image. And as a complex detection, we can consider image captioning. Image captioning problem is for every image we need to generate a sequence of words or a sentence which semantically describes the image, the interaction between the objects, and the actions which occur in the image. This is already solved problem, and it's called the image captioning problem. And there are a lot of different architectures, procedures, how we can deal with this problem. So we have an image, the image goes through certain processes, and at the end we generate a sentence to describe an image, the actions and the objects. But imagine if we already solved this problem for every image, we now are able to generate sentences. So what will happen if, as an input, instead of image, we consider a text? We have a text, we have a semantic description, and we want to generate image which is closer to this text, to the semantic information. So this is it. So here we come to text-to-image generation models. One of the main and major players in this field is DALL-E or DALL-E 2, when they stormed the community with their architecture of generating images from the text. The architecture is the following. We have a text encoder. The text encoder is an architecture where we give a text. We generate special vectors or sequence of vectors which represent our text in n-dimensional space. We have a similar encoder for image as well. We project our image pixel values into n-dimensional vector, into the same space which we have for text encoder. And the generation process, the image generation process occurs the following way. If we have a text, we encode it into n-dimensional vector or sequence of vectors. We can tune these vectors, distort the values of these vectors, modify them, and instead of decoding the exact vector which will give the same image we have, we kind of want to change the diversity of the image and to have different images which will semantically be closer to our text. That's why we have some procedures, distortions for our vector representations here. So now if we kind of already imagine how we can generate images from the text, so what it means to generate images with some specific styles. We have a prompt, we have a text, a dog in the park. We can generate totally different images with different styles, but the context, the semantic meaning will be the same. But the main difference here is the style. We have a style of Van Gogh style, neopunk style, line art, or something else. This is what we mean by saying generate images with some specific styles. To solve this problem, to kind of be able to generate an image with different styles, we need to come back to 1970s or 1980s, cover a little bit of background, how we can design a model which will be able to generate images. Back in 1970s and 1980s, people tried to solve a problem which was called the nosing problem. If you see in the first image, the quality of the first image is not that good. We have distorted pixel values. There are some dots, points in the pixel values. And all we need to do is to design an algorithm or any network which will be able to remove the noise from the image. And as a result, we expect to get a cleaner version of that image. So it turns out if we take a clean image and generate a random noise from any distribution, let's say randomness from Gaussian distribution, and add to the cleaner image, we will get the same noisy image we have before. So the problem is to design a model, to design an algorithm which is able to predict this noise. And if we're able to predict this noise, we were able to remove the noise from the noisy image and get the cleaner version. So now we kind of imagine how we can solve a denoising problem. And it turns out that the noise in the image has some strength. It means how strong the noise values distorted the pixel values. So imagine if we have a clean image, we added a noise like we've done before, and we added the noise a couple of times, over and over and again. And we have a totally different representation, which kind of looks like the same noise which we've sampled from a Gaussian distribution or any other distributions. So we already come to the denoising diffusion probabilistic model, which has two main procedures. The first procedure is the called forward procedure, where we add the noise to our clean image. And the second procedure, which is called backward procedure or denoising process, where we try to solve, to learn a model, to design any algorithm which is able to remove that noise. And here we design a neural network architecture to learn that noise, which has to predict the noise and remove from the image. And instead of removing the noise at once, we can remove the noise gradually in different steps over and over and again until we get a clean image. So here the image domain gets learned in the architecture which is responsible for image denoising problem. There are a lot of different architectures currently which try to solve text-to-image generation models. The majority of them are not public in terms of their codes, and in terms of their architectures are public, but the codes, the implementations are not available. The only available architecture is LDM, latent diffusion models, which was done collaborated with Stability AI. That's why they called stable diffusion. And today we will concentrate on that architecture mainly. The architecture consists of a couple of parts. The first part is image encoder, where we have an image mainly in 512 by 512 resolution. And instead of working on that big resolutions, before this architecture, people used to deal with the big resolutions, and it is kind of heavy, costly, and we needed a lot of computational power. And instead of working on the whole resolution, we can project this image into a smaller resolution, and where we have more chances to learn faster and learn more complex scenarios. An image decoder to bring back the original image from the latent representation. This representation, the projected representation, is called latent representation. Text encoder, because we are dealing with the text-to-image generation model, we're going to have to need a text encoder architecture, which again, we give a text. The main responsibility of that text architecture is to project the text into a representation in the latent space. And UNet architecture, which is the only architecture which is responsible for the predicting of the noise and removing of the noise from a noisy image. Now, if we already know how the diffusion denoising probabilistic model works, and we also kind of familiar with an open architecture, we want to discuss specialization of the style we want to learn. What it means. The original stable diffusion architecture was trained on the public data set, which contains a lot of images, millions or billions of images, image and text pairs, and which taken from the internet. And some styles are recognizable for a lot of people, and people may recognize a style because it is very known. We can find a style in the internet. But what will happen if we have a custom style? And we want to tune our text-to-image diffusion model so it will be able to generate images which semantically will be closer to our text, but the style will be the style which we customized. So those are the examples of the custom styles which we cannot find on the internet, but we want our model to fine-tune on. The fine-tuning, when we talk about the fine-tuning of the diffusion architecture or any text-to-image generation model, we expect to have this kind of results. When we give a text, we expect to generate some scenarios, different images with different variations, but the style will be closer with our image. We need some images which represent our style, because we don't have an ability to describe the style with the words. That's why we need to collect images, kind of describing what we imagine that our diffusion model needs to generate. The personalization or specialization methods currently we will concentrate on 3 different architectures. The first one is called Dreamboot textual inversion, and the last one is our solution, which is called specialist diffusion. The Dreamboot architecture is a plug-and-play method, which means the already existing method is flexible enough. We can apply this existing model on top of different architectures. We mentioned Imagen, LDM, Chameleon, or any other architecture. That's why we call a plug-and-play method. It is a fine-tuning approach, which means we have to train a certain parts of the architecture, mainly unit architecture and textual encoder, to learn our styles. And the third feature is the few shot method, which means we require a very few examples, 5 or 10 examples. This is very important because, as I mentioned, already existing diffusion models are trained on millions or billions of images and text, and if we want to fine-tune our method, we kind of gonna have to collect some images. And if those images are the number of the images are too big, that's not a good scenario. That's why we need a scenario where we will be able to generate only by providing 5 or 10 examples, visual examples. Textual inversion also has the same plug-and-play feature. It is applicable on different architectures. We don't have to have fine-tuning approach. Fine-tuning process, we only learn an embedding. We don't get into much details here, and it is also a few shot method which requires not more than 10 examples. Our approach, which is called specialist diffusion, it is also a plug-and-play. We can use this solution with different architectures. We have to train the unit and textual encoder architecture, and also the important part that we need no more than 10 examples, providing in our training sets. So what features we have in this architecture? When we talk about specialist diffusion, we can mention that by using specialist diffusion, we can learn any unseen style. Even this style is designed by ourselves. We want to fine-tune a model with our own style, which designed, drawn by ourselves. Also, it requires less than 10 examples, and the third feature is that we're going to have to wait roughly 30 minutes on a single GPU to learn our model. The contributions to design our specialist diffusion model is the following. We've designed the advanced augmentation method, and I think you are familiar with augmentation methods in terms of the with respect to the images, but we have advanced augmentation methods, content loss to solve a forgetting phenomenon, and also sparse time step updating, where we speed up the convergence procedure. Advanced augmentation method. I think most of you, if you are familiar with the computer vision problems, you already might be familiar with the image augmentation methods. There are a lot of functions where by using those functions we kind of diversify the distribution of our training set. And as we are dealing with the text-to-image diffusion model, we also have a caption with every image. Caption is a sentence which describes the image. The caption, to augment the caption, we have 3 different steps. The first step is called caption retrieval augmentation step. Imagine if we have a big, very huge data set with a lot of text, and we have text encoder which is able to encode this text into a latent representation, into a vector or a sequence of vectors. And for every text we have in our training data set, instead of using this text to fine-tune our method, we can retrieve this text from the text database and have totally different representation but with the same semantical meaning. This approach gives some diversification abilities, and by this approach we also generalize our model and avoid overfitting situation. Another augmentation method is called synonym augmentation method. In the text-to-image generation models, it turns out that the nouns or some attributes in our text, in our captions, play an important role. That's why we deal with them separately, and we want to replace the nouns in our captions with its synonyms. This is also a diversification method, so we will be able to avoid overfitting situations. The third method is called double augmentation method. I already mentioned that we have image augmentation, and when we change the image pixel values with different functions and we leave the text representation the same, the already existing architecture starts to ignore the text representation, ignore the captions, and only concentrate on the image, which is not the good in our case, because we want to force the model to extract some semantic information from the text as well and be aligned with the text. The generated images have to be aligned with the text representation. That's why we've designed the double augmentation method, which extends the already augmentation text with the representation of the image augmentation function. In this case, if we flip the image we used a flip augmentation method for the image, we extend our text representation with the description of image augmentation functions, which again is a diversification approach, and we have more abilities to avoid overfitting situations. But it turns out that this is not enough, because we have different problems, and one of the major problems in our case is the forgetting phenomenon. The first problem in forgetting phenomenon is that the images are not aligned with the text, not well as we expected. What I mean by not aligned, you see that we have a text, we have some nouns, some attributes which describes our text. We see in our generated images we have woman, dog, moon, even 2 moons, but we don't have a park. That's not good, because the images should be aligned with the text. In the second case, the same. We have a bird, a flying bird, but we don't have a bridge. Another problem in the forgetting phenomenon is that the domain gets very narrow and the diversification is not preserved. So we used content loss. The content loss is designed to avoid forgetting phenomenon and to force that the generated images should be aligned with the text. And by using this approach, we see that we were able to bring back the park, the representation and the pixel values for the park and also for the bridge. The sparse updating, when I described the diffusion denoising probabilistic model, I also mentioned that we have a denoising diffusion process with different time steps. Here is represented the time steps axis, and for the big T, it is convenient to use 1,000 time steps. But when we want to fine-tune our model, we have to learn the same representation for 1,000 time steps separately. That's why this is too much for us, and we want to have them to update them sparsely. And instead of updating the whole 1,000 steps, we choose different steps, usually uniformly distributed across the time steps, and only update our unit and text encoder architecture only on these time steps, which gives better generalization and faster convergence. So here comes the fun part. We're gonna need to check the results in specialist diffusion. In the left part, we have examples from our training data set. We also used to call the data set flat design, food doodle, and fantasy. And those are the generated results where we give different text. The generated images are semantically closer to the text, but in terms of the style, it is closer to the provided images. More examples from our results. If you remember, we had other methods, comparing methods, dream boot and textual inversion. You can check out that in almost 3 cases, our method is better than those methods. In the first case, they generated realistic images, but we expected different design. In the second case, almost the same. If you remember, I also mentioned that our model is a plug-and-play model, which is flexible to apply on top of different approaches. So we have a textual inversion architecture, our results, and textual inversion plus our, which means we combine the textual inversion approach with our approach, and we have some improvements here. Here we have representations. We have buildings here, we have clouds here, and etc. So to evaluate our methods and to be sure that our method gives better results than other competitive solutions, we also conducted a user study, anonymous user study, where users don't know which image was generated in which model, and we kind of ask the user which of the generated images aligns best with the reference image. The reference image is the few shot examples, the training data set we have, and by checking out the voting results, we see that our method is green, wins in all 3 data sets we have. This is the reference. If you want to check out existing solutions, so thank you. We have a Q&A.
About the sparsity of these types of the diffusion. What's the proportion of these steps? Like 10%. Regular 10%.
We have 1,000 time steps, but we update only on 10%. Yeah. T equals here in 1,000.
How do you define this number to be 23?
It is practical number. People have done a lot of experiments, compressive experiments, and the 1,000 turns out to be a good number.
Is there a reason why you focus on style transfer and not inputting objects into the latent space? I don't know the exact word for it. Like Dream Booth, where you also can put in a person and have that in the...
Yeah, but we don't, in that point, we didn't have competing architectures, but Dream Booth and textual inversion architecture is a way to fine-tune or personalize our style or object. We concentrate on the style, that's why we use them as a competitive architectures to compare with.
Yeah, thank you for the great presentation. I wondered if you measured the speed of your method and compared it with other state-of-the-art methods. Like, how long does it take to fine-tune the model?
In the Dream Booth case, and our method requires roughly 30 minutes on a single GPU, the same GPU with the same configuration, the same version of the libraries. In the textual inversion, a little bit less, 20 minutes maybe 20 minutes to specialize the style. Mm-hmm.
One more question. You said about this forgetting, and have you tried to learn several styles in a row or in one fine-tuning procedure? So you can generate in several styles just having one model.
So we learn only one style in one model. We don't learn different styles in one model.
Is there a reasoning for that?
Yeah, because the quality is good when we learn only one style in one model.
Can it be somehow fixed?
How to learn different styles in one model?
Yeah.
Actually, we try to learn different styles or different objects in one model, but the quality is not that good, not the good as we expected. That's why we have to choose one object or one style with the architectures I described. We have to change the architecture to learn different styles and different objects. Mm-hmm.
Thank you for your talk, but you can train like sequentially, right? Different styles. For example, you train, we concentrate on one style, training is done, you train another style, you have embeddings for both of them.
But we have a forgetting phenomenon. Forgetting phenomenon is solved for the objects, but forgetting phenomenon still lives for styles, and we can remain and preserve the style from this first style to the point when we learn the second style, but we will lose a lot of information if we talk about this specific architecture. Of course, we can solve the problem with choosing different architectures or designing another architecture. Mm-hmm.
What about photorealistic image of people for a model? How it's good based on?
To consider photorealistic as a different style, you mean?
No, I mean just like a real photo. You have no examples. I know that it's some problems with it.
Actually, it is out of our context because we want to learn any specific style. We can consider photorealistic as a different style and try to fine-tune our model on that style. But we haven't conducted any experiment with photorealistic, and I'm not quite sure that the quality will be preserved the way we anticipate.
Yeah, but I mean, what's the problem with this? I don't know, maybe 6 fingers or...
It is a totally different problem. We can solve the problem in a different way by preserving this style. We have to have additional architecture which is responsible to preserve the structures of the object.
How many styles have you considered when you perform this anonymous user comparison? And have you found any styles or groups of styles which show that this difference, this difference between the other methods?
We considered 5 styles, and when we conducted a user study, we gave them 3 styles, 400 images for each style, generated 400 images. The second question, could you repeat the second question?
The second question was if you have considered multiple styles, like hundreds of thousands styles, what would be the distribution of the differences between styles of your method and other approaches? So, if you have considered the three styles in this user questionnaire, then maybe not very representative to see the differences between them. The idea was that some styles or groups of styles may have features that are not very well represented with your method.
Yeah, I think I get the question. First of all, for 3 styles, we have 3 different models trained. We don't learn 3 styles in one specific single model. We have 3 different models. But in terms of the features of the styles, yeah, we have that situation that some styles are easy to learn, some styles are not easy to learn. And when we talk about the comparison, some styles are also learned in original stable diffusion architecture. When we talk about, let's say, a Van Gogh style. The Van Gogh style is easily learned, and the comparison, the measurement of the comparison will be closer to our competitive results. And I think maybe we need to conduct an experiment with the very hard examples, the examples which are not easy to learn. I mean, the hard styles. It's not easy to decide which styles are hard to learn. We choose a style, we fine-tune our model, the model is able to generate by preserving the style, and maybe we need to take a closer look how we can decide which styles are hard. Then to deal with the diffusion shifts. We don't have any experiments with the differences between them.
Could you please tell me what kind of practical applications are of your findings?
The practical applications. The practical application is the pure architecture is one of the example of practical architecture, practical application. And in our company, we have different scenarios where we can use that. If you remember, I'm from PicsArt. PicsArt is a company as a creative platform, and it means users tend to design their own style, and we want to learn their style, generate different images with their style, recommend the styles to different users, and distribute their creative art to different users. This is the example as an application.
Thank you again, Hazarapet, and thank you all.
Thank you.